All right, moving on. We have on our list, we got forces above the horizontal. Oh, there we go. We just did that. And now we're going to do the inclined plane. The inclined plane. You people are going to love the inclined plane. Okay, so here's what it is. The inclined plane means essentially something like on a hill. All right, something which is, we don't have a nice flat, horizontal, high-quality, made-in-America table. Maybe we have a table that's kind of tilted a little bit. Or imagine like a car on a hill or a box on a hill. And what happens in that case when we don't have that horizontal surface that we've been doing all the examples in before? Magic happens here, people. Magic. You're going to love it. Here we go. The inclined plane. All right, now, so I'm going to draw an inclined plane, a hill. And put our box not on table, but box on inclined plane table. Well, I suppose the table is just an inclined plane table. And so now what happens? All right, well, let's put some information in. Let's put down a couple of things that we're going to need. Let's say that the box has a mass of 10 kilograms. And we want to figure out the acceleration. So I'll put a question mark. So far, that's all we've been doing is figuring out accelerations. Of course, we don't have to. We can figure out any of these. We can figure out forces making something move. We can figure out forces holding something back. We can figure out the mass given the acceleration. We'll get to it. So here we have a box on an inclined plane. Now this inclined plane, we'll say, has an incline of 30 degrees. So 30 degrees. All right, inclined plane. Can you see it? 30 degrees, triangle time. Triangles do not go away. You got to get to know them. Don't fight it. We have an inclined plane, so we construct a right triangle out of it. So this is a right angle. And then now the first thing I'm going to do is I am going to draw a free body diagram with this object. Now, I can talk, right? The important vector that I have to draw, the important force vector right away is that force of weight. Now, earlier in the problems that we've done with the horizontal plane, okay, nice flat table, box on table, we never had to worry about that FW going down. At this point we haven't. We will. We'll come into problems where we do have to do that when we get to friction. But so far we haven't had to worry about the weight. The weight's really important in this bad Larry right here. So make sure that first thing we do is we construct a vector that represents the weight of that box. And weight vectors always point straight down toward the center of the earth. So straight down, that's our force of weight vector. So I'm going to write that as FW. All right, now, remember, we said it before, any vector can be broken down into a right triangle diagram. We just made a vector, and we are going to break this down into a right triangle. The weight is going straight down to the center of the earth. The earth is trying to pull that box right through that table. It's trying to say, hey, come right down to me, man, come right down to me. But it can't if the table's in the way. So it can't. So what the box is going to do is we know that if we lift this high enough or we have not enough friction, it's going to slide down the table. Now remember Newton's second law? F is equal to ma. The acceleration direction has to go in the direction of a force. So if this is going to slide down the inclined plane, there's got to be a force in that direction, or it wouldn't slide that way. F is equal to ma, that force in the direction of acceleration. So there is a force which is going down that inclined plane in order to make it go down that inclined plane. There's also a force into the board. I mean, like, boom, perpendicular to the board. There's pressure from the weight vector going into this board. And that is also going to have to be drawn in. So what I'm going to do is draw two vectors. I'm going to make this vector a dotted vector for now, because that means I'm going to actually move it. So I'm going to move that one. There is a vector that goes directly perpendicular into the inclined plane. So there's my inclined plane, and there's a vector that I draw perpendicular to that. That's called the Fn. F sub n. Why n? Because that means normal. That's called the n, the normal force. Now you might be thinking, well, what do you mean? It's like as opposed to abnormal? Like, no. Normal as in math. Math normal means perpendicular. When you say the word normal to a math instructor, they're going to go, oh, you mean perpendicular. That's why it's called Fn, because this vector is drawn perpendicular to the surface that it's sitting on. That's Fn. And there is force going into the board. Absolutely is. There is also force going down the inclined plane, which is going to make it move down the inclined plane. Now what I'm going to do is I'm going to take this vector, once I drew it with dots, I'm just going to keep it there. And I'm going to move it right here. See, I'm going to move that parallel right there. And the reason I can do that is because I am now going to construct a diagram, which is a triangle, a right triangle, which represents all the forces acting on that box. So I'm going to move this so I can get a triangle. Move this down here. And remember, we can connect vectors head to tail. Remember? We connect vectors head to tail. I've connected two vectors, the normal and the down the inclined plane. Now, down the inclined plane is parallel to the inclined plane. So I'm going to call it FP. So this is called FP. And this is a right angle. So that is the perpendicular to the inclined plane. And this is parallel to the inclined plane. And those two, perpendicular and parallel, would be 90 degrees to each other. So that's a 90-degree angle. And these are what are called the components of the weight vector. These exist because of the weight vector. Weight is trying to pull this straight down to the center of the earth, but it can't. So the best it can do is pull it down the inclined plane. So that exists because of the weight, and the pressure into the board exists because of the weight. So those two vectors are called the components of the weight vector. Every time we have an inclined plane, you have to draw that diagram every single time. So whenever we do inclined plane problems, and I will do at least one more, probably two more I'll do with you, inclined plane problems. The first thing we're going to do is we're going to make that triangle. Yes, we need it. And we also are going to have to figure out all the sides of that triangle. I know you don't like this stuff, some of you, but you are going to need Fn, Fw, and Fp to solve this problem. I told you you'd love these. Fun, huh? Okay, so back to the problem. What are we trying to do? We're trying to solve for this acceleration down the inclined plane. So we're trying to figure out how fast the Fp, that's down the inclined plane, will make this box, boom, will take off. 10-kilogram box. All right, let's put something else in here. Let's say, I'm going to put, there is a little bit of friction. Okay, let's say there's a little bit of friction. Again, we haven't learned how to calculate it yet. There's actually the next video. We'll learn how to do that, calculate that. But so far, we haven't learned how to do it. So I'll give you a number that represents the friction. Let's just say that there is friction holding the box back. Okay, remember, that's what friction does. So it says, no, stop, you shall not pass. Friction is Gandalf. Yeah, friction, Gandalf. So it's holding the box back. So I know the box is going to accelerate down the inclined plane, so friction is going to act against the motion going down the inclined plane. So I'm going to write that as F sub F, the force of friction. That's what we do. And we're going to give that a number. Let's say the force of friction, right up here, and I'll do it here. Force of friction is, I don't know, let's say 30 newtons. 30 newtons. Okay. I was actually doing some quick math in my head to give a number that will work. So hopefully that works. I've done the math right. So let's say the force of friction is 30 newtons. Okay. All right, let's figure out the acceleration of the box. Well, remember, the first thing you do is draw the triangle. Second thing you do is figure out all three sides of the triangle. You got to do it. So let's write those down. I'm going to put those over here. Okay, so Fw. We need Fn. And we need Fp. All right, Fw. That's easy. That's Fw is equal to mg. Mass times acceleration due to gravity. That's it. That's it. Okay. So what is the weight of this 10-kilogram box? Fw is equal to mg, which is equal to 10 times g, which is 9.8. So our Fw, this side right here, is equal to 98 newtons. That's going to be equal to 98 newtons. All right, that one's easy. Next, okay, we need to figure out this side of the triangle. Well, we only have 90-degree angle. We don't know any of the other angles. We can't do any of that trigonometry, sine, cosine, tangent. I quit. Oh, that is not the attitude. That is not the attitude. Okay, stop that. Shut this off. Go get some coffee or something, okay? Lighten up. You back? Okay, here we go. Now, this triangle is completely dependent upon this triangle. If we did not have an inclined plane, we would not have a triangle here. Those are called, in math, similar triangles. And we all remember that with similar triangles, angles inside those triangles are the same. They're the same. So the angles here are the same as the angles in the similar triangle that we already constructed. There's the 90. That means there has to be a 30 in here. And well, if this is 30 and that's 90, that has to be 60, right? So there has to be a 30 and a 60 in here. Can you see which one is which? That's the 30. So whatever, and remember this, whatever this angle is that angle at the top of that triangle that we constructed. It's always the same. So that's 30, that's 30. Now we have an angle, and that's going to be 60 down here. We can go ahead and do some sine, cosine, tangent functions to figure out those two sides. Let's go ahead and do that. So Fn, this is the one I would do next. I might need a little bit more room here. Fn. Okay, so this is known. This is the hypotenuse opposite the 90. That's my hypotenuse. So that's 98, and this is my adjacent side to the 30. So I'm using cosine. So cosine of 30 equals my adjacent side, Fn, over the hypotenuse, 98. If I multiply those, then I'm going to get Fn. So Fn is equal to the cosine. It's going to be around 86. But let's get an exact value on that. So let's go cosine 30 times 98 equals, oh, lies, about 85. So that's 85. So 85 newtons. So I'm going to put that over here. This is equal to 85 newtons. All right, let's get FP. That's opposite. And the sine of 30 is 0.5. So this is opposite, so I'll get FP. Yeah, well, let's do this. Sine of 30 equals FP over hypotenuse 98. So FP, 0.5 times 98 is 49. So this is going to be 49 newtons. Now we're ready to solve the problem. We haven't been solving the problem? Oh no, actually what we've been doing is just setting the problem up. We took all this time to set the problem up. So to set up any inclined plane, let's review right now. Okay? Any inclined plane, draw a triangle. Then you have to construct a second inside triangle with an Fn and an Fp. Then you're going to take that angle and put that angle here. They're always the same. Then you're going to figure out your three sides. Now you're ready to solve the problem. That was just getting ready. Now ready, but let's do this. Right here, see, this hasn't gone away. We're going to use this setup to figure out the acceleration. F net, force is making it move, force is holding it back. Set it equal to ma. Here we go. What force is going to make this move? Down the incline. The one pointing down the incline, 49. So that's 49, that's the one that's making it move. And look, the one holding it back, friction always holds you back, so friction is holding us back. And this is greater than friction. It will move down the inclined plane. 30 degrees is a pretty steep hill. So yeah, it's going to slide down that hill. Okay, so let's put that in. Force is making it move. Minus force is holding it back, which is our friction, equals mass, 10 kilograms, times A. This is easy. Actually, solving the problem is easy. Setting it up is the pain in the butt when it comes to these inclined planes. But you got to do it. Well, you don't have to. It's Merca, so you don't have to if you don't want to. But then you're not going to do very well. So, and you want to do well, don't you? Yes. Okay, so 49 minus 30 is 19. 10a. Acceleration is 19 divided by 10 is 1.9 meter per second squared. That's the acceleration of the box down the inclined plane. That is a basic inclined plane problem. We'll have more fun with these later. They get a little more complicated. But for now, we have now got the basics of our force problems. The basic, easiest force problems are the ones where we don't have to calculate friction or we don't have to solve for anything else but A. Then we'll move into more examples. But for now, we've got horizontal forces at angles with multiple forces in inclined planes. And from here, we keep on going. All right, that wraps up our basic force diagram problems.